Did space-time have a boundary at the Big Bang singularity, given that the universe is believed to have had zero size at that time? What were the boundary conditions at the beginning of time? Good question. Did space-time have a boundary? So we're talking about the Big Bang singularity. First of all, the Big Bang is the event that gave birth to the universe. That's the best theory that we have in cosmology. And this Big Bang event was not an explosion, it was an expansion of space-time. It happened roughly 13.8 billion years ago, according to the best information that we have. Some researchers would say that it could have been before that, maybe double the time. But the mainstream theory is that it happened 13.8 years ago. And the universe is believed to have been a vanishingly small point at the time, what we call the Big Bang singularity. Now, what was this Big Bang singularity? A singularity, from the perspective of general relativity, is a position. It is it is a location. It's Let's talk about time. You go back far enough in time, and the entire universe, the curvature of the universe becomes infinite, and the density of the universe, matter and energy density of the universe, becomes infinite. That's your Big Bang singularity. Now, in mathematics, singularity, when you have a singularity, it essentially means you're dividing something by zero, which is unphysical, and it actually indicates that your theory is there is some flaw or deficiency in your theory. So maybe there was something else, maybe not a singularity, but the best theory that we have says that there was a singularity, which then expanded, and it gave rise to the universe that we have today. So the expansion happened in different, let's say, stages. I mean, we look at it from the perspective of stages, but overall it was just a smooth expansion. Not entirely smooth. You had inflation, which happened a fraction of a second after the birth of the universe. You had the decoupling of the forces and all that. So that's what happened. Now, what was the geometry of the universe? What was the shape of the universe? Was there something beyond the universe? Was there a boundary between the universe and what is not the universe? We don't know. We don't have sufficient data. There are these theories. There is a theory put forth by Stephen Hawking, the late Stephen Hawking, and Hartle, which says that there was no boundary. And it says that when you go back closer and closer to the moment of the Big Bang, then time itself becomes fuzzy and it takes on spatial, spatil, the aspect of space. So there's a theory like that. And so basically what I'm saying is that the physics of the very early universe is very poorly understood. To properly understand the physics of the very early universe, let's say in the first second after the Big Bang, you would have to develop a quantum theory of gravity, which incorporates quantum effects with general relativity. Because when the universe was that small, all the physics was quantum physics, right? Because that's the ultra microscopic domain, the quantum domain. So and at that point in time, you would have a unified force, a single force, which then decoupled and other forces decoupled and the symmetries broke, and so on. So you would need to develop a viable quantum theory of gravity, which includes general relativity as well as quantum mechanics, quantum field theory, and we don't have that right now. And because of that, the physics of the very early universe is very poorly understood. First of all, because we don't have sufficient data. We have data. What data do we have? We have the cosmic microwave background radiation, which came much later on, which was created, which emerged out of the universe, out of space-time much later on. So overall, we have very little understanding of what really the conditions were like at that time, and that's why it is not a question that we have clear answers to, but it is a very fascinating question, and it is questions like these that fascinate physicists and drive research forward.